So here we are with our first bit of further statistics, and the first topic in further statistics, at least for Edexcel, is discrete random variables. Now, if you're following the Edexcel course, you will have met discrete random variables, hopefully in the early stages of your A-level studies. So this topic should be at least some way familiar. But I'm going to go basically from basics, but we'll obviously move quite quickly through these. And I want to start with a definition. So a discrete random variable is, and you can read this through with me, an event which has a finite countable number of outcomes. So there's the discrete bit. An event of some sort can take a certain set number of possible outcomes. So you can kind of quantify and count and list all of those kinds of key mathematical words, what the outcomes of this event would be. But it's a random variable. So the way that those events, those outcomes are cropping up is happening in a non-predictable way. So it's not a sequence of events. If outcome 1 happens, then outcome 3 will follow. It's any random, I shouldn't really use the word random, should I, given that it's in our definition. Any outcome of the event, I can't predict what it's going to be. And that's a really, really complicated way of describing quite simple ideas in certain cases. So for instance, the roll of a dice. So in a non-biased dice, so standard die, we would expect the numbers 1 to 6 to appear on the faces of that die. And we would expect an equal probability for each one of those. So a 6 for each one. And this is just one way, this table is just one way of representing a discrete random variable. So across the top, we've got the possible outcomes for this event, the event being a rolling of a dice. And then we've got the associated probability for that outcome. So the numbers 1 through 6. Now, this particular event, this one would be uniform, and that's because every one of them is the same. So this is actually a uniform distribution here, but they wouldn't have to be. So a very simple extension of this would be that the dice is biased towards certain faces or certain numbers, in which case the probabilities would be different depending on the numbers, and you wouldn't have a uniform distribution anymore. Let's look at the example then, just to make this a little bit more interesting. So really, this is the kind of key way that we could describe this information, but you could get represented your information as a kind of a formula to describe the probability. So they could tell you that the probability is equal to 1/8 when x is 1, 2, 4, or 5. You can see what I've picked a slightly more complicated version here, and 1/4 when x equals 3 or 6. So that's just another way of representing the same things. These two things are obviously equivalent. But here's a question for you then. So if this was the distribution of, say, a dice that we had, and I rolled that dice 100 times. So I'm going to roll the dice 100 times, and then I'm going to take all of those results, so all of the 100 rolls, and find the average score. What would that average be? So I think it's best if you pause the video and have a little think about that. You're rolling the dice 100 times, and then you're going to take those 100 outcomes, add them all up, and average them effectively. What is that expected average going to be? Well, what we essentially are anticipating have happen is that these faces are going to appear with the frequency of the probability effectively. So we would expect a 3 1/4 of the time, and the same with a 6 actually. So we would expect to have 25 3s and also 25 6s within those 100 rolls, because we're expecting a 3 to crop up 1/4 of the time, same with a 6. Given that all the other probabilities then are half of that, we would expect, I mean, this isn't right, is it? We can't have 12.5 1s, but we can sort of mathematically, if you will, and certainly in terms of an average, and 12.5 2s, and the same with 4 and 5, of course. So this would give us the grand total of all of the throws and their summed total, which I believe is 375. So when we actually find our average score then, if we roll this dice 100 times, is 375, the total, divided by 100, which is 3.75. Now this idea has, this is the expected value, and we can actually work this out more directly. We don't have to know a certain number of throws. We can work out the expected value of any distribution just by working it out directly, effectively. So what we're saying here is the expected value, notated with this capital E, is basically the average of the outcomes you could have weighted according to how likely they are to occur. So 1 occurs 1/8 of the time, and 2 occurs 1/8 of the time, and 3 occurs 1/4 of the time. This is technically my 25 divided by 100 here, so there's my quarter. My 4 1/8 of the time, my 5 1/8 of the time, and 6 1/4 of the time. And if you chuck that in a calculator, and I did actually just pause the video to triple check, because you never can be sure when you're doing maths live, we do actually get 15/4, which is our 3.75. So there's that same expected value, and you can see that that's going to happen no matter what our number of rolls is. This is actually independent, not dependent on, of n, the number of throws. So you could use this kind of to just understand what the average expected outcome of this particular distribution would be, whatever the size. We can formalize this, and in fact we should formalize it to give us something that's a bit more mathematical. So our expected value then can be defined as the sum of each individual x value, so that's what that I there subscript represents, the individual values of x, multiplied to the probability of that value of x. So we took each of those numbers 1 to 6 in the previous example and multiplied them to their corresponding probability, so the probability directly below them. So that's what that one's saying there, each individual x value multiplied to its probability. We can actually do something similar with the variance, and we should probably just sidebar very slightly and just check we remember what a variance is in a normal situation. So for any data, raw or grouped, when we work out the variance, we would do the sum of the values squared over n minus the mean squared. Of course, then you would square root that for standard deviation. Similarly here then, the variance is the sum of the x squareds, but again, because we're dealing with a probability distribution weighted according to the probability that they occur by, rather than dividing by a total number of numbers, and then minus the mean squared, so our e of x squared. Now this notation doesn't look particularly nice, this x subscript I squared, probability of x, so on and so forth, but this has the same structure as the expected value above. It's just that you are performing that operation not to each individual value of x but to its square, and so we call this e of x squared. So the variance in a discrete random variable probability distribution of this form is the expected value of the x squareds minus the expected value squared. So just pay really careful attention to where those squares are in that expression. I'm sure you can imagine, but a really common error that occurs in the exam because you're rushing or you're panicking and you're not meaning to be sloppy, but of course it does happen, is that you forget to subtract the mean squared. You just subtract the mean, or you don't square each of your individual values when you are calculating your variance. So you don't do 1 squared times by the probability and 2 squared times by the probability. You hop, skip and jump your way through and miss some of them out. So even though it's a really basic formula, do make sure you're doing it accurately. Okay, so I'm going to jump to quite a big example. If you are not ready for that, go and find a textbook. It's a series of questions online. Go and practice your way up to an example like this. But this is knocking on the door of an exam style question here. Laid out a little differently from what you might expect from Edexcel, but not beyond what you should be able to understand. So we're told that for a random variable x, which takes the numbers 1, 2, 3, 4, and 5, the probability of 1 is the same as the probability of 4. The probability of 3 is twice the probability of 2. Probability of 5 is 0.12, and the expected value is 2.89. And then we're just asked to complete a table of probabilities, and that's it. So I think the first thing to do is to mathify the problem. So I know it's already written in a lot of maths, but it's not in a sort of format of maths that we would expect for these sorts of questions. So I think the first thing I would want to do is write out the information in a format that makes more sense for discrete random variables. So we know this variable takes the values 1, 2, 3, 4, and 5, and I'm now going to use that information to fill in the table. So I know that the probability that x is 5 is 0.12. 1 and 4 have the same probabilities, so we could call those A. They're going to be the same as each other. And the probability that x equals 3 is twice the probability that x equals 2. So if the probability of 2 is B, then the probability of 3 is twice B. We're then told that the expected value is 2.89. I'm thinking simultaneous equations with a question like this because I've got potentially multiple unknowns depending on how you've set up your equations, certainly in this case. And if I've got multiple unknowns, I need at least 2 equations in order to be able to solve them simultaneously. So I should be able to create one out of the expected value. So don't forget the expected value is the sum of, so adding up all of the individual x values multiplied to their probabilities. So we could work that out. So that would be 1 times by A, 2 times by B, 3 times by 2B, 4 times by A, and 5 times by 0.12. And we know that that total equals 2.89. And of course, just simplify that a little bit. And I've got one equation in terms of A and B. What about for the other one? Well, here's where I think you need to lean back on your A-level understanding of this topic, and you would be expected to retain that information. That would be assumed knowledge, especially when you come to your final exams, because you will have either taken or be about to take your A-level alongside your further maths. And of course, with these sorts of distributions, we know that the total probability has to be 1. That is a fairly standard result, and we're going to use that to our advantage. So we know that the sum of all of the probabilities must equal 1. That's the standard result for discrete random variables. So we know that A plus B plus 2B, that again, plus A plus 0.12 is 1. So 2A plus 3B is 0.88. I now have simultaneous equations, and in a situation like this, it's likely, shall we say, that you could just use your calculator to solve these. Given the type of question, given the amount of marks and where they're going to be allocated, it would be unusual for method marks to be awarded to simultaneous equations here. I say it would be unusual though. There may be a situation where these are actually quite complicated simultaneous equations, in which case there are marks awarded for the method. And I would hate for people to miss out on marks because they couldn't be bothered to write an extra line or 2. And that is it. For a method mark for simultaneous equations, I would expect to see something like an equation rearranged for one of the variables, and then it's substituted into the other equation. If at that point you then had used your calculator and jumped to the answer, and there had been a mark for the simultaneous equations, I would humbly suggest you probably got the mark by that point, because you've written an equation in just one variable. It's up for you to decide whether that's a bit of time that you're prepared to spend on the off chance there's a mark there, but I think it's worth knowing about. When you solve those equations, you get the value of A 0.17 and B as 0.18.